Hello, everyone. My name is Tracy Hartledge. On behalf of Chiral Technologies, I want to welcome you to our presentation, Implementation and Utility of Daicel sub-2 micron chiral stationary phases for ultra-high pressure liquid chromatography. Presenting today is Dr. Weston Umstead, Technology Manager. Dr. Umstead graduated from Daicel University in 2011 with a BS in Chemistry and Biochemistry, and from the University of Denver in 2016 with a PhD in Chemistry. Dr. Umstead has been with Chiral Technologies since 2016, where he started working in our Definity Genomics group on the development of fast and reliable PCR cleanup products. Now, as the technology manager, he is responsible for new and emerging technologies, Definity Chemical Services, and the core technical team, who are responsible for our in-house chiral screening and separation services. During the presentation today, members of our technical team will be on hand to answer questions you submit through the presentation dashboard. Please click on the Ask a Question button, and you can write in your questions and receive a written response. Please feel free to reach out as questions arise, or we will also be having a Q&A session following his talk. As always, you have the option of reaching our technical support team by emailing questions@cti.daicel.com at any time. Please note that a copy of Wes's presentation is available in the handout section of your menu. Along with the presentation, we have included information on our column selection service and application notes on our sub-2 micron columns. Enough from me. Please give your attention to Dr. Umstead. He will take over now. Wes, the floor is yours.
All right, good afternoon, everyone, or good morning, depending on where you're located at. I appreciate your introduction, Tracy. And so as you are all probably aware, we are going to be talking today about Daicel's new sub-2 micron chiral stationary phases for ultra high pressure or ultra high performance liquid chromatography. So to begin, here's just a very brief outline of the different topics that we're going to touch on. I think it's important that we start off with an introduction on chiral chromatography. Some of you may or may not be familiar with some of the background in terms of the mechanisms for selection and how chiral chromatography works in general. So we'll start off on the same page regarding that. We'll then do a very brief history on UHPLC and the theory behind sub-2 micron. We will do some things that you need to consider when you're going to be implementing sub-2 micron and using UHPLC, and then we'll end with a lot of different examples using Daicel's new sub-2 micron columns. So to start off, just a very general background on chromatography. There are three different components to any chromatographic system. Obviously, you have your column, you have your instrument, and then you have your chromatographic conditions, your mobile phase composition, additives, things like that. Now, each of those components has a set of unique parameters that kind of affect its overall performance. So for instance, the conditions are controlled by the mobile phase composition. The overall length of the system is controlled by the column, or is related to the column. And then the instrument can only perform as well as the sampling rate of the instrument is designed to sample. So in some cases, though, there are multiple components that can be affected by the same parameter. So for instance, pressure is related not only to the length of the column or the particle size of the column, but it's also related to the actual conditions. So a higher viscosity mobile phase naturally gives you a higher pressure. And in some cases, actually, a component or all three components are affected by the same parameter. So your overall analysis time is affected by your sampling rate, the length of your column, and the strength of your eluent for the chromatographic conditions. So if you look at all of these things put together in kind of a triangular Venn diagram, as it were, you can see there's a number of different terms, as I mentioned, that are unique to just each individual component, but you've got some over here, selectivity, for instance, which is related to the column and the chromatography. And then right smack dab in the middle is resolution. And the resolution is not only affected by the three components of the chromatographic system, it's also related to N, which is the plate count, and that is directly related to the particle size. And so that's why we are here today. We're here to talk about particle size and how using sub 2 micron ultimately increases the number of theoretical plates, and as a result of that also ends up improving your resolution. So if we look at particle size development over the last few decades, it's been something that has been continuously evolving essentially since the inception of chromatography early on. So in the 50s, uh, the best that the industry had to offer were irregularly shaped particles that were 100 micron or even larger. And if you tried to pack them in a column, you're looking at maybe 200 plates if you're lucky. When HPLC kind of started in the 60s, in the late 60s, we were dealing with 10 micron as we wanted to try to improve our resolution and improve our efficiency. We were able to get smaller 5 micron particles, and you were also able to get more symmetrical, consistently shaped particles, which helped with column packing. You're probably all aware of superficially porous particles, so they came out in the late 90s, early 2000s, and we began to move into sub 2 micron right around when UHPLC was launched in 2004, with sub 2 here in 2003. And the biggest improvement, as I pointed out already, is in the number of theoretical plates. So we were at 200 plates early on. We can now achieve things up to 32,000 or even more depending on the particle size and the efficiency in terms of packing. So Daicel, back in the 80s, when Daicel acquired this technology of polysaccharide chiral stationary phases from work that was done by Professor Okamoto from Japan, we started developing stationary phases on the particles that were most reliably available, which was 10 micron. And then we slowly progressed into 5 micron, 20 micron for preparative scale, 3 micron, and now we have obviously our sub 2 micron particles as well that we'll discuss a little later on. Initially, a lot of the work was focused on the chiral selectors, and so if you go back to Professor Okamoto's original work, there's a number of selectors that were there. And now we're obviously starting to look at how can we make our products a little bit more applicable to the market and reacting and being preemptive in the types of demand that's coming from you, the user. But if we look at the chiral selectors, this is just a screenshot of some of them from our chiral selector poster, which is free. If you go on our website, there's a link there that you can get one of these sent to you yourself. But we have 39 different chiral stationary phases. And of those 39, there are 34 unique selectors, 5 of which are available in coated and immobilized versions. So if you look, for instance, here at IA is 3,5-dimethyl triphenyl, 3,5-dimethyl phenyl carbamate. It's the same selector as AD, except AD is coated amylose, and chiral pack IA is immobilized amylose. And so I already made the distinction. You've got amylose and cellulose. In yellow here are your cellulose-derived stationary phases, and in blue are your amylose-derived. That's important because, for instance, if you were to screen a compound against IA and IB, although they're the same selector, you oftentimes will see very different selectivity or separation ability depending on your compound. And so what is different? Really, you're talking about the difference in the linkage between the individual glucose units. So for cellulose, you've got a beta linkage between the different subunits, and in amylose, you've got an alpha linkage, which doesn't necessarily seem like it's that large of a difference, but when you actually look at the separation ability, as I said, you can see in some cases separation on one and not the other, or separations on both. So in order to determine what selector you actually need, we generally will apply a brute force screening approach where we will take a number of different selectors, our chiral pack and our chiral cell selectors. We'll screen it on a number of different mobile phase combinations: normal phase, reversed phase, polar organic, extended range, which is basically an extension of normal phase, except they are mobile phases that are not compatible with our coded columns. So the first generation of phases listed here are your ADs and your ODs. O's for our chiral cell, or O being for Professor Okamoto, so a little bit of homage to him there. And then our ADs and whatnot of our amylose phases. These phases can be, they're just coated on the silica gel surface. And so things like THF and dichloromethane will actually dissolve the polymer off of the silica gel. So those are your extended range solvents. And then you've got your immobilized second generation, which these are resistant to that same effect with THF and DCM and whatnot. So these can be used in those extended range normal phase conditions. And we also have a number of specialty selectors as well, which we really won't touch on in this presentation today, but we have the protein phases, your AGP and your HSAs. You've got your ligand exchange, your crown pack, your crown ethers, your Lindner phases, as well as the relatively recently developed zwitterionic Zwick's phase. Now, the reason we have so many, as I said, there's really no good way to predict what the interaction on the column is actually going to be, and that's because you've got a large number of possible chemical interactions that can take place, electronic interactions that can take place. This is just a very short list of some of those. When we're dealing with chiral chromatography, most often we're talking about hydrogen bonding, steric hindrance, pi-pi interactions, and dipole-dipole, either induced dipole-dipole or dipole-dipole from some interactions within the molecules themselves. So if you look at just kind of a sample, this snippet, this would be a cellulose backbone here, and based on the chiral selector, this is actually OC stationary phase. You can see that there are a number of different possibilities for interactions. You've got the amide here, so you've got your carbonyl and your nitrogen, which can hydrogen bond. You've got your phenyl group, which can pi stack. And then when you actually have this polymer coated on the surface, the polymer doesn't just exist as a linear form, it actually twists on itself, and so you end up creating these chiral grooves, which then adds a secondary level of interactions, which makes it even more complicated in trying to predict which stationary phase will work for which compound. So I'll touch on these chiral grooves in a couple of slides here, but you can see it gets more and more challenging as you actually look at the structures of these compounds. In general, though, what we like to use is what's called the three-point interaction model. This particular example here, this Eason-Stedman model, is designed more for chiral drug interactions with a drug binding site, but it illustrates the same principle that you have your drug binding site, or in our case, a chiral stationary phase, which has 3 points of interaction. And then you have your active enantiomer, and then your inactive enantiomer, or in our case for chiral chromatography, your active enantiomer would be the more retained enantiomer. Your inactive one would be the one that kind of comes through quickly. You've got the points on your compound which line up well with the interactions on the stationary phase. And so this active enantiomer, this more retained enantiomer, interacts with the stationary phase differently, and they elute at different phases, different times. With your inactive enantiomer, obviously here you can see that everything doesn't line up perfectly, so it's not as strongly interacting with the stationary phase, and even if you were to rotate it, you still have a mismatch, and so it ends up eluting faster as a result of that. This is a little bit more of a bulky diagram, but it represents basically the same thing. This was from a review article done by Professor Lammerhofer, and probably a little bit more representative of what is actually going on in the system. You've got your chiral selector, which is solvated by whatever your solvent is, and you also have your enantiomers, which are solvated to some degree, depending on their interactions. And in your ideal fit bound state, as things are kind of coming through, your solvent is displaced, and your active enantiomer, in this case your S enantiomer, is interacting strongly with your stationary phase, and your non-ideal R enantiomer is only interacting perhaps in one location and still solvated in some other. So you kind of get the point. 3 points of interaction is desired for a good recognition on your stationary phase. So if we go back to the chiral grooves, which I mentioned before, this is the same selector. This is our phenylcarbamate. So this is OC, cellulose, and then it's the same selector on amylose. When the polymer itself actually twists, you've got these chiral grooves. In cellulose, it happens to be a 3/2 left-handed twist, and in amylose, it happens to be a 4/1 left-handed twist. And so depending on how your compound can actually come through and interact with these different grooves, it will determine how strongly or not strongly it interacts with the stationary phase. And here's where you can illustrate the same selector has the possibility of having different interactions with the polymer because there's a different number of twists. So if you look at something like prilocaine, prilocane's got 4 predominant interactions that it can have with the stationary phase. You've got hydrogen bonding, pi stacking, dipole-dipole stacking, and then steric inclusion. And so again, if you're looking, this is OC, we're actually going to look at our newer phases, our immobilized phases. If you were to do a screening on normal phase, so hexane IPA with 0.1% DEA, since this is a basic molecule, if you were to screen this on IA, so IA is our 3,5-dimethyl phenylcarbamate on amylose, you really don't have any separation. You're getting a little hint of separation here. Your alpha is 1.04. Alpha of 1 is considered separation. Alpha of 1.2 is baseline separation. So you're not there at all. If we were to keep the same selector but change to cellulose as the backbone, now you're starting to see pretty good separation. It's not quite baseline yet, but then if you take it one step further and change the electronics of the selector from 3,5-dimethyl to 3,5-dichloro, which is IC, still cellulose, now you have a very strongly retained pair of enantiomers. So you're going up almost to 20 minutes versus 10 minutes or so in your IB and your IA cases. Your alpha is 1.25, so very good baseline separation. And all by changing the polymer from amylose to cellulose, and then changing the electronics from from methyls to chloros. And so you can't really model this. Again, it goes back to the point I made when I first started this. You kind of have to employ a brute force screening approach in order to see what combination is going to work best for the compound that you have.